Welcome back to High Performance Computing, Advanced Scientific Computing. Today we have our lecture 6, Parallel Programming with OpenMP. So this lecture really is getting advanced in terms of programming models, and we will leave the space of so-called distributed memory programming that we had the last times with MPI and these message exchanges. Here we're talking about shared memory programming. But before we dive into the material of that lecture, let us review what we had the last time. And there we had really a practical lecture where we explored a little bit the ideas of Cartesian communicators, where we explored also data structures. And we basically have seen that in the Cartesian MPI communicator, we have really a good helper for simulating different regions. And our key example was always basically having, for instance, the ocean simulated and then maybe doing a wave propagation of some sort across the ocean. And in order to compute this correctly for one, let's say, party of the domain decomposition, you would be always basically required to communicate with your neighbors, because you actually have to say to your neighbors, what is your own, wave height, and also, of course, other physical properties. Normally, I simplify here a little bit with this wave height. Of course, you can imagine wind speed and other factors also play into the game. Still, also as a kind of part of the domain, I'm also interested in my neighbors around me. So it's not only that you have to broadcast basically around you what is the current situation of your own domain. In order to compute in the next time step, maybe your own wave height, you're also depending on your other neighbors. And this is a good example of using a Cartesian communicator. And we had one example where we basically used then this so-called Cartesian shifts in order to enable basically a message exchange. But we also learned that the shifts really just represent the preparation in order to understand where I am in the Cartesian world and how I then combine this with real MPI send and receives. And this is usually a kind of block in the understanding of students. So here, think about again, when we create this Cartesian communicator, we basically shifting, and this means just preparing basically the message exchange. I still have to do some MPI communication operations to really get data across. And with this, basically, we come to something we will also explore more in your assignment when we talk a bit about an ocean simulation, of course, in a very simplified fashion, but still basically capturing the essence, how you would simulate a real world problem. The second part then of the practical lecture was going through some MPI derived data types. I don't list them here again. I think they became pretty clear with the examples that we had of contiguous or also the vector that we had by just extracting a column out of the bigger matrix or the triangle that we had then to make the indexed working. Here I show you a little bit again also what we had the last time, which was then alluding to a very powerful binary file format called the hierarchical data format, which is often used in scientific and engineering application. And we learned in a way you can see it as a file system of sort within a file. In other words, if you have here a concrete example, if we dump its content of basically this Bremen small data set that we had as an example that we use in AI basically for the clustering method, here we have this different ideas of more or less directories, if you want, thinking about a file system, but in the end, it's of course a structure of the part in the data set. We looked, for instance, in the clusters, we have seen many basically in the beginning were zeros, and once this DB-scan was running, which is a parallel version we maintain and which is based on MPI and also on HDF5, obviously. So there we basically use this module load that we have seen the last time executed here with 4 nodes, but you also realize instead of basically having our own program compiled and then used, we just rely on the module here to have an MPI version DB-scan already compiled that we can use. We also learned that the Bremen small was obviously just the smaller version of a bigger picture. You see here the amount of bytes is actually much less than the real data set in Bremen, which of course then really requires high performance computing. What it does was essentially a good application area where you have laser scans. A car that you see here is basically going through the inner city, doing laser scans around it. And then we come to something called point cloud based on basically reflections. And of course, there's lots of noise you see around the cars, obviously is noise, but also windows will be hard here and there. So in order to recreate the city that you see here, which is the inner city of Bremen, really, we do this clustering, in this case, a DB-scan clustering. And of course, we will review a little bit more the clustering all over the course. We come back to this even in the hybrid. And today we will learn that you even can use this with shared memory. Obviously, if you go shared memory, then it will be quite restricted because in the end, you're just within a node if you want to do it. And we will have a look on this today. So today we carry on with a very practical topic. Again, we have something which is kind of a de facto standard in HPC, really. OpenMP is known by almost everyone who is in the HPC community. It's basically an equivalent of MPI, but in the shared memory space. And we will learn what that means and connect it to our introduction lectures again. Also here, there will be parts on the assignment, which you have to do with OpenMP to basically recreate some of the examples. But also I will basically next week on Monday demonstrate you again in practical lecture 6.1. Of course, all the examples that we kind of introduced today more conceptually. And then I provide you some demos in the practical lecture 6.1 as usual. So we start with understanding again shared memory and the idea of parallel and serial regions, which are often introduced by so-called sentinel. We have to understand the fork and join of so-called master and worker threads. We describe a little bit OpenMP as a standard, really, of course, and then this would enable portability. And in order to see a bit bigger picture how these basically also, let's say, improved over time, we look in something called Comps and PyComps that is actually extending here and there with Omps, also the OpenMP future really of the standard, which is much more into data flow and task-based evolutions, also considering GPUs, for instance. Then in the second part of this lecture, we go to real concrete examples for OpenMP. Parallel programming basics, you remember we had this interesting C files that we want to look in. And of course, now instead of programming MPI, we go from a C file and then program OpenMP. And you will see that lots of OpenMP statements are really compiler directives. So they influence the compilation of the program. So they don't really represent something we would say as message exchanges, because in the end, it always assumed to have access to shared memory. With this, you have some trouble here and there, race conditions, for instance, where you need critical regions or single regions, and there's a need for synchronization that we will explore in the second part of this course today. There are, of course, some comparisons with MPI, just thinking about also performance issues with load imbalance, which can equally happen also, of course, in the OpenMP domain. And then some application examples, but as I said, also HPDB scan and so on, we will do this much more as an example also in practical lecture 6.1 when I demonstrate it. And of course, parts of your assignment will be also using OpenMP here as hands-on so that you really get the idea of this particular important standard. And with this, really, you have another complex aspect of parallel programming. It goes without saying we could have a whole week of OpenMP programming in this course. And of course, the idea of this course is not to be OpenMP only. That's why we call it high performance computing. And there are lots of topics that entail basically these subjects. But of course, OpenMP is something what you really have to learn if you stay in the HPC community and be an application developer. Usually, this is a equal often used standard at MPI. And we will also learn in lecture 7 then, probably next week on Tuesday, that you actually combine these today with MPI and OpenMP. So you're ready to really work and program HPC systems with scientific application, and with this also doing kind of parallel computing on different levels. So let's see what shared memory is about. What are the programming concepts? Here you see basically the two varieties that essentially shared memory systems can have. We call that the unified memory access and the cache coherent non-uniform memory access called CC-NUMA. in a way, all of those would have the ideal picture that you see on the top. You have some RAM here, some shared memory, and you have different threads. That's how we call that. It's a difference to MPI where we call that processes. Here we call it lightweight threads. And basically they have always access to a shared physical address space. That means there's no need for doing message exchanges. They communicate, if you will, through the memory. And this is an idealized picture. Obviously, with UMA and CC NUMA, you have rather these pictures where here you see the memory is equally accessible to all the processes and CPUs really, and then you would see that's kind of uniform. But there are also specific bus interconnects that would do the CC NUMA ideas of really then ensuring on behalf, basically on the developer that want to have shared address spaces, of course, which you see is not existing here, but it enables this with so-called very specific cache coherence protocols. And it's still, let's say, programmable as a shared memory system, although you see it's not really it. Important is to realize this kind of lightweight notion of this processes that we really call thread here. That's an important part in shared memory programming. So with this, of course, you can have the power of, let's say, the speed that really memory entails. And this is high performance. And with this, you have, of course, also different access to this caches when you basically be and working with the memory within the node. And this is, of course, a very good idea because it uses more or less this flat memory model where you have lots of latencies and bandwidth that are really all the same for them. That's where we call them also symmetric multiprocessing sometimes. And of course, now, if you have then this CC NUMA, it is a bit different. But as I said, also, it's kind of more or less one single address space where you as a developer think it's one memory, but in the end, it's really through this coherent link, basically physically distributed memory, but you don't really realize it because this established link is there. And basically you have still then more aggregated memory than you could possibly have with one single address space here in this particular example. So these are, let's say, more varieties of shared memory and how it is represented on the real hardware, right? And with this, we come to the question, what means now the shared address space? How can I envisage this? And you see here two the examples would have two work items to basically work on some certain program. And it actually enables immediate access to all data from all processors, right? So let's assume this processor wants to read essentially something what the first processor just dumps into memory. That's always possible. And that's actually the same true when you have this, as I said, CC NUMA. Basically here, it's still one shared address space, what you can do. Here's a sort of example, if you would think of a simple example of so-called thread communication, which is not really a real communication. As I said earlier, basically you write data and you read data here into the memory of the own, let's say, private data space of each thread. We come to this private areas in a moment, also to understand how this is developed. But you see that basically thread 1 is putting here this value into the shared address space of data, and then the other thread can just read from it and here do a +1 on it as one example. And this is, of course, a little bit then the idea of using the shared address space for many different data sets for data inside the node. And with this, you have, of course, the real good idea of using all the different layers of caches here, for instance. On the other hand, you can imagine it is limited because in the end, we cannot go out of this boundary box here, right? If there's CC NUMA or you have this UMA, in the end, you're limited to the amount of memory that you have on both of these sides. And going off the node would require you to do MPI. And that's what people actually doing in hybrid communication, but this is something for later. So what is OpenMP then? So it's basically something which is a standard. There's an OpenMP API specification really existing. You can see that here in the different URL. And of course, there are different implementations that here is basically available and that we can use for really working with OpenMP. Usually, the threads are very central and there's this so-called work sharing idea of this, between the different threads, and then use always constantly basically the shared address space where the data is then and is basically communicated through the different threads. They can be synchronized. They're basically a lightweight process that shares a common address space with other threads, but are not really a big, bold process that we know from the normal, let's say, Unix idea. So here it's less costly, basically, than really having a process running. And the idea is really to think about this of using independent computing again once more, so that you can basically have small executions of tasks performed independently from each other. And we will have some examples now in these, let's say, small applications that will follow. The way how it works is basically that you have always a master thread. So this is the one that is, so to speak, the master in terms of executing your C program. And within the C program, you basically would start doing so-called pragma statements. Here, the sentinel, if you also call it, and to initialize really what's happening in parallel, you always would have a pragma statement. And there are different pragma statements that we will learn about. But you see here how that is then realized. You have the sequential part with the master thread, and then there will be a fork of different number of threads in the parallel region. And this will be then joined again to a serial region. And there could be another parallel region of the core that is actually having perhaps even less number of threads. And then you collapse again with join to a serial region. And this goes on and on. You see another example, no matter if you do it in Fortran or in C, the same idea applies. So in the end, the compiler directives are then an important part of it. And again, it's important to understand here that the master thread has always a very special role in this, which is marked here a little bit. You see the master thread is kind of always existing and going through this whole statement. And the interesting thing is you program it a little bit in a way that you don't know how many threads will actually execute this, right? So here you would have the number of threads that can be different in each region, but you'd never really explicitly usually program for it. You see that here you have a certain function, you enter a pragma statement, and then you don't see here how many threads should be really used. This is done in the job script usually. And we will come to this in a moment. But by doing this, what's coming out of that is that we then actually executed as many as we have specified, of course, and the number of threads in the job script, which could be then this team of threads. And basically, they basically go to sleep, if you want here, these different threads before you come to the next parallel region. And this is an important part to see, that there's always this parallel region and the serial regions where it makes sense. Thinking about portability, and of course thinking about that OpenMP is a standard, we also want to see why is that so and why it is so important. Now again, very similar like we had in the basically MPI or OpenMPI implementation library. Here we have the OpenMP library that essentially enables us to go from one HPC machine to another HPC machine somewhere else. Let's see, from Barcelona to Jülich, from Jülich to France, CEA or so. It is basically a certain standard that mostly really works. Of course, here and there, portability has limits. And the best limits to be understood is, of course, that you cannot do this with all HPC related systems. One good example would be here this D-Wave quantum annealer. That is, for instance, now also something where we really work on in daily practice, but there OpenMP is not really supported. So it's more for traditional HPC machines that basically almost all of them, I would say, in the world have OpenMP libraries installed. And for this, you usually can assume that your OpenMP application should probably work on these different systems. And now you understand how this is now reflecting a little bit when you thought in the beginning of the lecture series. We have these 4 basic building blocks with theory, technology, architectures, and software. So software is here the OpenMP library. The architecture needs to be really, from the hardware point of view, the kind of shared memory architecture for a certain part, let's say within the node. And then, of course, the technologies, which means we have here the computing We have the different elements of maybe caches. And so that enables a lot of powerful work within the node, because essentially we should have their very fast system. With MPI, we always, basically go between the different nodes, but each node in itself, of course, by doing shared memory, captures the essence of all the different cache hierarchies and the speed, instead of usually basically just doing MPI within the node, which doesn't really make sense. And there you basically already have the theory. In order to achieve a speed up, you maybe even would be, combining both, of saying you do MPI between the nodes, and then of course within the nodes you do shared memory OpenMP. So it is the de facto programming model OpenMP. It is basically, of course, just for shared memory applications, but we will gonna use it, and we want to use it because it then really tries to really get the best out of the node. In theory, you could of course use MPI there. There's no problem in that. It's just not very smart to do so. So, and to put that in a bigger picture, and what you will learn in lecture 7 then is really to combine these. You see here, essentially CC NUMA elements per node that are then basically the shared memory nodes we have here, that then have, of course, a communication network between the different nodes, InfiniBand and so forth, where you then really do shared memory basically within this part here, and then would be via the network interface communicate with MPI then over the wire here to the next node in order to get data here. And as I said, you could in theory do this MPI also here from processor to processor, but it really doesn't make sense. If you remember, it does a buffer of the message, so another copy of the data that you anyway can access through the memory. But we will talk about hybrid programming much more when we come to lecture 7. So let's say this is just a kind of small appetizer. And what I said to you here, to really thinking about on-node communication, that is what I just explained here, right? In theory, you could do this, but it means to have duplicates in memory of data, not only the send buffer, you remember, we had also the receive buffer. So with this, you have lots of memory space allocated for something which is not really required, because essentially shared memory can read the memory directly on the same node. And again, when I think to just give some pointers here for people that are very interested to do this rather small scale programming of OpenMP, and also MPI and many other examples of tutorials are really given here in the praise portal that you have, in terms of many tutorials around OpenMP, MPI.io, MPI, OpenMP tutorials you see here from videos from different partners around the world that unite basically in our HPC community. Obviously, I cannot really do very much here in this course, because OpenMP is just one part of the bigger picture, and we have to basically give you a broader picture on what HPC entails. But if you're interested in, for instance, working on your own laptop with OpenMP, you can do so and have a look at these videos. Now, basically, then doing this hybrid programming obviously is not that simple. That's why we have a whole lecture around it. And we're also thinking about, can we support that a little bit with more patterns of that support parallel programming? We already were alluding a little bit to stencil methods, if you remember, with using the heat equation in the room and so on. So, and exchanging, of course, data from the previous time step to the next time step, which is one of the key ideas. And the performance of hybrid code is not as simple as, of course, doing just MPI or doing just OpenMP programming. By combining both, you have to be, very clear in when you do the kind of transfer between the nodes, when is the right time for this to prevent basically load imbalance within the node, and then of course also when you have waiting send and receives across the nodes. So very interesting way, of course, however, to get the best performance out, because in the end, you have the good power of the node that you can use and speed up essentially by using the shared memory, which is of course the best performance you can get if you can read and write to memory directly. And then of course to go over the limits basically of this memory, because in the end the memory limit is here in space, right? But I have here across the wire then MPI, while I do OpenMP here with the CPUs and accessing directly the memory. I can use then the MPI standard in combination to exchange some crucial ideas basically across different nodes. So when you assume that could be the ocean that we were representing, and we have a domain decomposition, let's say of 4 parts somewhere in the ocean, you can imagine that the tile within the ocean, the wave height and everything within the ocean would be computed with OpenMP, but exchanging this data of the wave height and so on needs to be done with MPI then, so that can it be computed also in all the other nodes. And hence we need there more or less patterns that apply certain functions to this domain decomposition that we entail in order to really work well, and to also for the programmer to think about scaling and that this really works. One key example there is basically, again, our DB-scan algorithm. You see, we come back to this again and again, and you basically get more and more understanding, I hope, of this part technology. There will be still basically a lecture where we go a little bit more in detail what this clustering is now really doing. But you can imagine here, so you see another example. That's what DB-scan does. It will identify even those which are here intertwined, that these are 2 different clusters. And that's why we do this here in the inner city of Bremen, as I already was pointing out. And here we use really MPI and OpenMP to scale better. You see here the linear scaling, really on increasing the number, of course, more and more, and achieving a speed up where you have a pure linear scaling here, the optimal that usually you can't really achieve. But what you want to do is a near optimal or near linear scaling. And you see here with MPI, at some point in time, the performance drops off because you have lots of message exchanges, of course, in order to exchange the halos, as we learned the last time, and so forth. And with hybrid, you usually are better off. DS1 and DS2 actually are 2 different data sets we're talking about. And you see with a hybrid approach, usually you're a little bit better, although here's a tail off of some sort. But for some data sets, it's really getting better. Obviously, it depends a bit how the distribution of the data sets is and so forth. The other motivation here for this, I was just pointing out here, that actually you can use this obviously with MPI alone. That's what I showed you last time in practical lecture 5.1. But you can also do essentially here the idea of specifying within the job script the kind of number of threads. And then, of course, you have to also allocate here on the nodes the number of tasks you want to do per node in this regard. So in this sense, you can do different nodes, and within the nodes, you have different tasks that actually then are executed on the node, which then do the OpenMP, while, you know, basically we can have message exchanges across these different nodes with MPI. And essentially the rest stays a little bit the same here. Obviously, when we compile this is a bit different here and there, what I show you later. The other idea then, when you think about kind of OpenMP and the idea of programming, brings us to the next situation where we said, okay, quantum computing is not possible, but what is about GPUs? So is OpenMP ready for GPUs? And you basically say a new standard it is. And there's also a standard that is derived a little bit from OpenMP called OpenEgg. I will show you a little bit. So obviously we will do and hear more about this accelerators in generally in lecture 9, really. But there's a kind of movement around to improving this OpenMP standard. And you can imagine there was a world without accelerators, and people have used OpenMP, and now there's a world with accelerators where, you know, different versions of so-called Omps, basically in our research domain, is basically exploring in research projects usually how that could look like. You see here a bit the evolution, how prototype of tasking, task dependencies, loops slowly move into the OpenMP standard over time, and where we are nowadays, and then basically improving this OpenMP standard over time to also nowadays basically have not only a better data flow, but also this heterogeneity that we know. Because, you know, and remember from my earlier lectures, GPU programming is different, right? Here you see OMP target device CUDA, indicating that probably an NVIDIA GPU lying around here, but we just cannot usually like rely on that. We firstly, if you remember, have to go through the main memory of the CPU to the device memory, so that the, let's say, many cores within the GPU have really access to the data. And with this, you need the standard to be aware of this kind of copy of, let's say, the data from the main memory space to the device memory space, and then get later the results here from the device memory back to the host memory, which is here a little bit this copy out and so on. Obviously, that would require much more explanation, and you don't need to know all the details here. It just tells you that OpenMP is not standing still. Although it's a very old standard, a very traditional standard in HPC, it is also a standard that, you know, is evolving over time. And this is essentially driven by many different research projects. The DEEP project, for instance, was working on Omps and different versions of it. And of course, with this, one can look on other elements, because if you are already on this kind of more fine granular view, right? We're thinking now that we not anymore have this big, bold processes. We have lightweight threads that execute some form of a task. And these tasks can be different tasks. We will talk about this: data parallel tasks, functional parallel tasks, and of course, having lots of data dependencies. And with this, you have now access more or less to a very idea of a task that needs to be executed no matter what is happening before or around it. So what do I mean by this? It could be, for instance, a large execution tree that you have, right? So we call that maybe more or less a data flow or workflow that you see here in this explanation, just roughly explained, where you basically have then applications that probably run with the Omps model in order to really just want to have a much more simpler way of working with these task-based programming constructs, where you think about much more the data flow should be optimized. And of course, here we see that these elements also get more and more in the OpenMP industrial standard over time. The simple idea, however, remains. You have still Pragma OMP, the Sentinel, working on these statements in order to enable parallelization. And then when you have this kind of so-called multi-dependencies from these tasks, you can imagine that different elements what you would do. And here we see, for instance, that of course, here we do a full parallelization of all the elements. You can do similar like we had a little bit maybe with the kind of idea with communicators and breaking them in different groups. You can do different task dependencies. This is multi-dependencies on different parts, because here it might be functional parallelism. So each of those are doing actually different part of tasks, but they all together basically achieve the full picture. And there are many different examples how you can use, which actually reflect how people are actually using OpenMP for solving problems within a node, for instance. And this is, of course, quite nice. And in the end, it's also something where in the future, perhaps it's not anymore so important to exactly know where the task is. So you have a whole execution engine that it can optimize your task placement, that can optimize the use of caches over time. Because in the end, what the kind of application developer here is interested in using this programming model and basically just rely on a certain task description as a workflow or so. And then the execution engine, really the runtime, will then make sure that this is nicely parallelized and placed. If you see already the ideas how that works with Pragma, and we will come to some statements later, you will see anyway that the idea of programming it is very straightforward, because you just do a compiler directive. I mean, the name of the idea of saying just a compiler directive is a bit loaded. We will see in the second part of the lecture in the examples, it can be quite tricky here and there, but still it's not the whole big MPI program where I basically have to do a lot of, let's say, twists to the parallelization. I'm responsible myself as MPI programmer to do the parallelization. Here, the OpenMP runtime and also Omps and so on, they all have this kind of inherent part of parallelizing this in a way automatically, of course, using this compiler directives. And then, as such, it's a very powerful model. And here's one example how that could basically be used. Here's the Comps, which is a comp superscalar. It's basically a framework that really is now the idea that maybe you go even one level up, where the PyComps does the same for Python bindings, where perhaps you basically see a code that is now really leveraging not only, let's say, one node, but also multiple nodes, distributed fashion nodes, so that you become more or less the high-level developers, and you just think about where is my data and where can be some tasks, but the totally details on this is basically figured out by the engines underneath. And this enables us then for applications in different infrastructures like clusters, grids, or cloud computing, even with EC2, where you still have some APIs how to connect to, but it's more coarse-grained programming model, right? And much more larger in the view, because here we're thinking about already going, of course, again, in a distributed fashion and helping there a little bit. But while doing so, still having the idea of the same syntax in a way, and also having the idea of the basically possibility to think task-wise and not basically message exchange-wise as we would do it in the MPI space. And this was really just the first lecture to warm you up a little bit, to have you basically told you a little bit about the bigger picture of OpenMP and surrounding elements, starting from shared memory aspects up to the new developments in Omps and so on. Here we have an interesting simulation, and you see it's almost alluding to what we had the last time also with MPI. Of course, you can do the same with OpenMP. You see here one ocean wave example that has been programmed, actually, interestingly enough, with OpenMP. So you see here nicely the wave propagation I was alluding to in the last lecture and also in this lecture. When you think about that, this is of course not computed by one thread. With OpenMP, you compute this with different threads. Here and there, scientists, we want to know something about the domain we basically representing or analyze. So that's why you will see this interesting thing that suddenly there are red waves where you would say it's actually wrongly modeled. But of course, we are interested in a scientific perspective and view on it. So meaning it is basically going maybe over some certain thresholds here with the velocity of the waves. And this is usually a scientific application, although it looks pretty real. For once, the reality is not the main driving factor in a sense. It's also the scientific reality that is behind it. It should not look very nice only, it should be accurate and correct. And by enabling here the connection to visualization, you see also you get a much better understanding what we actually simulate and what we can do with these standards. So we stop here for a short break and then come back to really crafting our first OpenMP program. See you then.